Welcome back to The Explainer. Today, we're stepping into the super fascinating world of environmental forensics to look at a highly specific, very technical protocol. It's called EPA Method 5F. Honestly, you can really think of this explainer as a chemical detective story. Our main objective? To find a really specific air pollutant hiding right inside the chaotic mix of gases and particles bellowing out of industrial smokestacks. By the way, if you enjoy geeking out on the rigorous science behind everyday environmental protection, please hit that subscribe button to join our community of focused learners. It really helps out. Okay, grab your lab coats because we've got a mystery to solve. So, it all starts with a pretty fundamental challenge. Think about it for a second. How on earth do we measure something we literally cannot see? When we look at stationary source emissions, which is just the EPA's term for fixed pollution sources like power plants or factory smokestacks, we aren't just looking at one simple chemical. We are looking at this wild, microscopic soup. You've got gases, heavy metals, volatile organic compounds, and tiny particulate matter all completely mixed together. Our job today is to figure out exactly how scientists actually manage to pull one specific type of invisible needle out of that very chaotic haystack. And here is our prime suspect. Non-sulfate particulate matter, or PM. Now, what's genuinely wild about this is that our target analyte doesn't even have a formal CAS number, that unique numerical ID assigned to basically every chemical substance out there. It doesn't have one. Why? Because non-sulfate particulate matter isn't just one single chemical. It's a broad category defined entirely by what it isn't. It's literally just whatever particulate matter is left over after we account for all the sulfates. So to quantify it, we can't just run a scanner and look for it directly. Instead, we have to use this brilliant, methodical process of chemical elimination. To crack this case, we've got a really clear 5-step roadmap for today. 1. The pollution problem. 2. Gathering the equipment. 3. Collecting the sample. 4. The chemical analysis. And finally, 5. Calculating the results. Okay, let's dive right into this. Section 1. The pollution problem. Finding the needle in the smokestack. Section 2. Gathering the equipment. Setting up our forensic toolkit. Look, to achieve flawless, legally defensible chemical separations, you definitely can't just use standard kitchen gear. We need a highly specialized forensic toolkit to pull off this extraction without contaminating the evidence, right? The setup is incredibly precise. We need 125 milliliter Erlenmeyer flasks, specifically with ground glass joints, so we get a perfect airtight seal. We pair those with an air condenser to carefully boil liquids without letting any of the precious vapors escape. We also need a whole array of volumetric flasks for exact dilutions, but the absolute MVP of this entire equipment list, the Ion Chromatographer. This machine is incredible. It's essentially the super sophisticated filter that uses a specialized column and a conductivity detector to physically resolve and measure the exact amount of sulfate ions we separate from the rest of the sample. Moving on to Section 3, collecting the sample, securing the crime scene. All right, our very first active move is to head straight up to the smokestack itself. We have to gather the raw particulate matter directly from the source before it has a chance to disperse into the atmosphere. The EPA mandates 3 absolutely crucial physical steps here. Step 1, and this is a big one, is to withdraw the sample isokinetically. Big word, I know, but it basically just means we have to pull the gas into our sampling nozzle at the exact same velocity that the gas is already traveling up the smokestack. If we pull too fast or too slow, we end up collecting the wrong sizes of particles, and our data is ruined. Step 2 is temperature control. The filter has to be maintained at exactly 160 degrees Celsius. Guys, that's over 300 degrees Fahrenheit, hotter than you'd bake a cake. We have to keep it blazing hot so that water and other volatile gases don't condense into a liquid and wreck the particulate evidence. Finally, step 3, we carefully take that loaded filter back to the lab and extract the sample using water. Which brings us to Section 4, the chemical analysis, interrogating the evidence. Okay, we are safely back in the laboratory. This is where the real hardcore detective work happens. We've got this filter covered in a microscopic soup of particles, and we need to force this mixture to give up its exact chemical makeup. Remember our main challenge from earlier? We cannot easily measure our target, the non-sulfates, directly. So we use a brilliant little trick. We meticulously measure the exact amount of sulfate present in the sample using that ion chromatograph we talked about. Then we take the remaining sample, add a very specific chemical, ammonium hydroxide, to neutralize it, dry the whole thing in an oven, and weigh the resulting mass. By figuring out exactly how much sulfate we have, we're basically teeing up our final deduction. Let's quickly look at the timeline for this extraction because honestly, it requires some serious patience. At hour 0, we cut the sample filter into small pieces and drop them into a flask with water. Then, for the next 6 to 8 hours, we place the flask on a hot plate and gently reflux the contents. Refluxing just means we heat the liquid to boiling, but we use that air condenser to catch the vapor, cool it, and drop it right back into the flask. This 6 to 8 hour boiling cycle is absolutely vital. I mean, it's essentially a full workday spent watching water boil, but it ensures every single microscopic bit of the collected sample is dissolved and pulled completely out of the filter fibers. Only after 8 long hours can we finally cool it down and let the solid materials settle to the bottom. Now, rigorous science always has a backup plan. What if your lab doesn't have a super expensive ion chromatographer just sitting around? Well, Method 5.5 provides a pretty clever alternative procedure in Section 16 of the manual. So we have our high-tech, conductivity-based primary method, but we also have an alternative, the baryon perchlorate titration. This one involves passing the sample through an ion exchange resin, adding a chemical called a Thorin indicator, and carefully dripping in a titrant until, boom, the solution turns a very specific visual shade of pink. Both methods are completely valid, which just goes to show there is definitely more than one way to corner our chemical suspect. And that leads us to Section 5, calculating the results, the final deduction. All right, this is the climax of our explainer. This is exactly where all of that meticulous lab work, the endless 8-hour refluxing, and the precise chemical separations finally translate into hard, actionable regulatory data. Before we get into the complex formulas, just look at how beautifully simple the underlying logic of the entire method is. It's just subtraction by elimination. If you take the total particulate weight that we dried and weighed earlier, and you simply subtract the sulfate weight, which we calculated as ammonium sulfate, what you are left with is the non-sulfate particulate weight. That is literally it. Total minus sulfates equals non-sulfates. And this brilliantly illustrates how the EPA translates that simple logic into some pretty rigorous mathematics. This is equation 5F2. It's the exact formula mandated to calculate the mass of our ammonium sulfate suspect, which is represented by the variable ms. It takes the peak height measurements from the Ion Chromatograph, that's HS for the sample and HB for the blank, multiplies them by a specialized calibration factor, S, and factors in dilution. Put it all together, and it gives us the exact weight of the sulfates in milligrams. But what if you went with the backup titration method, the one where we looked for the pink endpoint? Well, you get your own specific formula, equation 5F-6. Notice how different this math looks. Instead of chromatography peak heights, this equation uses the variable N for the chemical normality of the baryon perchlorate titrant and V for the varying volumes of liquid used during the titration. But here's the cool part. Despite using totally different variables, the math operates to arrive at the exact same crucial answer, the precise mass of the sulfates. To make sense of all these different equations, the EPA kindly provides a sort of decoder ring. We have a few key nomenclature variables to keep track of. The absolute most important one for our ultimate goal is right at the top, M sub N. That is the mass of the non-sulfate particulate matter. That is the true identity of our suspect. And right below it is M sub S, the mass of the ammonium sulfate. By calculating M sub S through our chemical analysis and subtracting it from the total, we finally reveal M sub N. The mystery is officially solved. So the real takeaway from this explainer isn't just about memorizing random chemical formulas or lab equipment. It's about recognizing the downright incredible lengths to which scientists will go to measure the invisible. We really have to ask ourselves, how do these standardized step-by-step chemical methods actually shape the air we breathe? Every single day, rigorous, behind-the-scenes laboratory protocols like EPA Method 5F are forming the very foundation of environmental protection. Without the ability to perfectly measure these microscopic pollutants through careful deduction, we literally would have no way to hold stationary sources accountable. So next time you step outside and take a deep breath of clean air, maybe remember the unbelievable detective work happening in the background to keep it that way. Thank you so much for joining me on The Explainer, and hey, keep asking questions.